theorem is the left inverse of an element in a group is also its right inverse. Right inverse. So it's proof. Let A inverse be the left inverse of A in a group G dot. Let E be the identity element or simply identity in G. Let E be the identity in G. A inverse A is equal to E. This is one. As you know that by the property of identity element, as A inverse belongs to G, A inverse operated with E gives you the A inverse, and it is same as E operated on A inverse. This is 2. This is by the property of the identity element. By the property of identity element, or simply identity. By the property of identity, and this is due to and the 1 is due to the fact that A inverse is the left inverse of A. We need to prove that. To prove that A inverse is also the right inverse. Inverse of A. That is, for this it is enough to show that A operated with A inverse gives the identity element. Okay, 3. That means we need to show A inverse gives us the identity element. Let us see what is the value of A inverse. So we take A inverse operated on A inverse. Using the associative property, we group these two elements, A inverse A operated on A inverse, and this is equal to A inverse operated on A is E from 1, so gives E operated on A inverse from 1 using 1. Now E operated on A inverse from 2, E operated on A inverse gives us A inverse, so it is A inverse using 2. Now again we may write A inverse as A inverse E. We may write as A inverse E using 2. Again using 2. So we have A inverse operated on A inverse gives us A inverse E. Now by applying left cancellation law, we get A inverse equal to E, which is 2, which is 3. That is 3 holes. Hence, A inverse is also the right inverse of A. Means the left inverse and the right inverse are the same in G. Next we prove reversal rule for the group. So let us understand what is reversal rule. If you are familiar with the matrices, then you know that if A is a matrix and B is another matrix, then transpose of AB, the product AB, transpose of the product gives us the B transpose A transpose. That is, when we are taking the transpose of the product, then the position of A and B get reversed and with their transpose. That is, we do not obtain AB transpose as A transpose B transpose. We obtained the result by reversing their position. So when we take transpose, the position of A transpose and B transpose get changed. So this is called the reversal rule. So similar rule obeys in group. So what is a reversal rule in group? Next theorem. For this we prove next theorem. The inverse of a product, the inverse of a product of two elements of a group is the product of their inverses, of the inverses taken in the reverse order. So meaning AB inverse is same as B inverse A inverse for all A and B belongs to G. So let us prove theorem. Proof. Let G be a group and E be the identity in G. Let A inverse and B inverse are inverses of A and B respectively. Before that, you may assume that let A, B belongs to G, and A inverse and B inverse are the inverses of A and B respectively. So, to prove that, AB inverse is equal to product of the inverses in the reverse order, means B inverse and then A inverse, that is B inverse A inverse, that we need to prove. Since B inverse is the inverse of B, so B inverse B equal B inverse gives us the identity element, and since A inverse is the inverse of A, so A inverse operated on A gives you A inverse is E. This is 2. Taking product of AB with B inverse A inverse, and this is equal to, we apply the associative law, that means we change the grouping. A then B inverse and then A inverse. This is A. B inverse is E from 1. So this is identity element using 1. Again A, again we apply here the associative law, that means this 2 is taken as first, then A operated with A inverse, and as you know that A inverse is E, so E by using the second, using 2, so we obtain AB operated on B inverse A inverse gives us the identity element. This is 3. Now again we take B inverse A inverse operated with AB gives us, change the grouping, A inverse A B, and this gives us the B inverse identity element B. This is using 2. And this again you may apply this B inverse operated with the identity element gives you B inverse, and again from 1 we obtain the identity element using 1. Hence we obtain B inverse A inverse AB is the identity element. This is 4. Now from 3 and 4 you may observe that AB operated with this B inverse A inverse gives you the identity, and B inverse A inverse AB gives you the identity. That means from 3 and 4 we have AB operated on B inverse A inverse is equal to, the identity is equal to B inverse A inverse operated with AB, and this shows that this element is the inverse of AB. It means B inverse A inverse is the inverse of element A dot B. It means it is represented as AB inverse. So hence we prove that AB inverse is equal to B inverse A inverse. Hence the result. So we may generalize this result. What is the generalization? Generalization is that if we take A, B, C, D, any number of product of any number of element, and if we take their inverse, then what we obtain? The inverses of the elements, and then we, like in the order of D inverse, C inverse, B inverse, and A inverse, like this. That means the product of inverse of the product is equal to the product of the inverses taken in the reversal order. So this is the generalization of the reversal rule.